Hello, so welcome to the final of the videos on astronomy, and this is where we're going to talk about evidence for the Big Bang. And so you need to be aware of kind of what the past evolution of the universe is in a very, very vague way, and what are the main arguments in favor of the Big Bang theory. Describe the evidence that supports it. So it's kind of saying the same thing almost again, but it helpfully says we're interested in redshift and cosmic microwave background radiation. And then a bit familiar from what we talked about last week, which is what the redshift in light received from galaxies sort of tells us and how it behaves, and explain why that provides evidence. So actually, a lot of this just restates the same kind of points several times, and you just need to be able to talk about redshift of galaxies, CMB. You don't need to know a huge amount of the Big Bang beyond sort of what we've got here. So if you've seen the TV show or listened to the theme tune, it begins in a way, our whole universe was in a hot, dense state, but nearly 14 billion years ago, expansion started. Wait. Then some fast lyrics and stuff. So this is our current idea about how old the universe is. About 13.77 billion years, although depending on what measurement you take, it might be plus or minus a billion, but not that important. And the idea is that at some point in the past, 14 billion years or so ago, the whole universe was in a tiny point. It's called a singularity. So all of matter exists in one little dot. Everything is there. Okay. And the thing is what on earth are the properties of the universe when it's all compressed into one dot? We don't know. How long it was like that? We don't know. Why it stopped being like that? We don't know. What was there before it? We don't know. This is basically a box of mystery that we do not understand, and potentially we may never. But that's what modern physicists are doing, is constantly pushing out boundaries to try and get some kind of understanding of what was like there. And then the whole universe expanded, and after a while, eventually it became cool enough. After about 400 million years, it became cool enough for stars to start forming out of nebulae, galaxies to form, and basically from this moment onwards, so actually from about here onwards, 325,000 years, we're pretty confident of the physics that happens here. This is physics that we understand, and we're generally happy. We're generally happy all the way over here. There's this weird stuff called dark energy, which again we've got no idea really what that is. It makes us feel good because we've given it a name. Basically, at the edge of the universe, things aren't behaving as they should. Just sort of confused people there. That's a terrible picture. Maybe I should delete that. And so we have this, but generally we're pretty confident on this year. Now the thing is, the Earth only turns up 4.5 billion years ago. So the Earth sort of appears, I don't know, sort of about here in history. That's when the sun sort of forms and the Earth forms, and then humans only really turn up about here. So in the last couple of 100,000 years. So it's actually, where on earth does this number come from, and why do we believe in it? Well, the first sort of idea of this comes from the first piece of evidence, which is the redshift of galaxies. Okay. So now remember that redshift is something we observe whenever a source of light is moving away from us. We see these lines which are shifted towards the red end of the spectrum, and that tells us that things are moving away. And the idea from this started the evidence with Edwin Hubble. And what happened is Hubble, in about 1929, okay, he is looking at galaxies. He's looking at galaxies at various distances away. And he's measuring very, very, very long distances. And he's measuring quite a lot of them. But I'm going to imagine here are some galaxies. Here's the first galaxy. Okay, and then here's the second galaxy. And here's a third galaxy. Okay. And he's able, via the work of a woman called Henrietta Leavitt, he's able to measure distances. Now, these are meant to all be about the same. We measure distances in space. They're very big. There's a thing called a parsec, which is about 3.2 light years. But we're measuring distances in a thing called 1 megaparsec away, and this is another 1 megaparsec, and this is another 1 megaparsec. Okay. Now, you don't need to know what a megaparsec is, but it's about 3.16 million light years. So it takes light. So the light that we're seeing from this galaxy has taken about 10 million years to get to us. This one, about 6 million years. This one, about 3 million years to get this distance. And he's measuring their distances, but he's also able to measure, because of their redshift, their speed going away from us. And what he finds is that the further away the galaxy is, the faster it is going. Okay, and more interestingly like that is which is kind of odd because it means there's no random distribution. The things that are further away are traveling faster, and he's able to measure the speed. And roughly, something that's about a megaparsec away is traveling away from us at around about 70 kilometers per second. This second one is going to be traveling at about 140 kilometers per second, and this one here is about 210 kilometers per second. Hubble notices that the speed at which galaxies are moving away from us is proportional to their distance. Okay. Now, Hubble knows that there is a very, very basic physics relationship, which is speed is equal to distance over time. Okay. And he decides to think, actually, if everything's moving away, what happens if you rewind time? Or to be precise, what happens if you do? Time is equal to distance over speed. And it turns out that this galaxy here, which is traveling away from us for 70 kilometers per second, and is, as of now, 3.16 million light years away, or 1 megaparsec away, if you try and work out, well, how long would it take for something to travel this distance if it's traveling at this speed, it turns out that for all these three galaxies, the answer is 14 billion years. And it turns out that's the answer for pretty much every galaxy that we look at. The speeds of these galaxies are such that actually, at some point, if you rewind time at a point 14 billion years ago, what you would end up with is, we rewind time, then 14 billion years ago, actually, all of these galaxies would actually be on top of each other. They would actually be on top of us. And this idea is the idea of what gives us the first indication of the Big Bang, this kind of measurement, that this redshift of galaxies means that at a time 14 billion years ago, they would have all actually been here, all on top of each other. And that is the kind of the first idea, the first indication in the 1920s that there is a beginning to the universe, because there's a point in the past when pretty much everything is in one spot. Because if you think of it forward, if you think about all these galaxies setting off on their journey, we hit the go button. Well, this galaxy is traveling fast. It's running 210 kilometers per second. So after a certain time, it ends up here. This galaxy is traveling slightly slower. So after the same amount of time, it ends up here. And then this galaxy, and that third one, ends up here. So all just from measuring distances, measuring speeds, and using time as distance over speed. Now this was the first sort of hint that there might be a beginning to the universe. Okay, so the redshift of galaxies. Now it's always important to actually, if you're asked what is the evidence, this term here of galaxies needs to be clearly stated. You can't just say redshift. You've got to say redshift of galaxies. This important. So the redshift of galaxies, the redshift of galaxies indicates that about 14 billion years ago, all of the matter in the universe would have been in the same place. Okay. Everything that we see is moving away from us. So this, the fact is that because all these galaxies are redshifted, it implies the universe is expanding. So as everything is redshifted, it implies the universe is expanding. Now, just as a quick little note, it can make the way this diagram is set up can make it feel as if, for example, that we are special, that we are at the center of everything. But actually, this is just a trick of relative velocities. So let's imagine an observer in this galaxy here. So someone is here. I'm going to draw them kind of in blue. Okay. So someone here, and they're looking at us in our galaxy. So our galaxy, we're kind of here. What would they see? Well, they would see this galaxy being the one moving that way at 70 kilometers per second. They would see this galaxy moving that way at 70 kilometers per second, and they would see this one moving away at 140 kilometers per second. So it's not that we are in a special place. Anywhere you pick, when you look out into the universe, everything appears to be moving away from you, because we always like to think of we think of ourselves as being stationary with respect to ourselves. So it's not, and here, an observer here would see this one moving 70, and then, so everyone would see the same thing because everyone thinks they're stationary. Now, this implied that there is a beginning to the universe, and that led to the idea of what we call the Big Bang theory. Okay, so the idea is that at this point, if all the matter was condensed into a small point, then what you would have is a hot, dense sort of mass of things filled with exotic particles and radiation. So the universe at the beginning being hot and dense and filled with high energy gamma radiation. Okay, so now this is the prediction. If you compress the entire universe to a small point, you have something which is very hot and very dense. Now, although redshift is a very convincing argument for the fact that the universe is not static and that it's expanding, the fact that no one has any idea what the Big Bang, no one understands the physics of this breaks all laws of people understanding it. So physicists at the time didn't like it. And even though this was discovered in 1926, and Einstein's theory of general relativity turns up around this time, and there are solutions of that say the universe should be expanding. There was a Belgian physicist who used Einstein's laws to suggest an expanding universe, and when he presented that to Einstein, Einstein famously replied to him saying that his mathematics was adequate, but his physics was abominable. Einstein himself would actually fudge his own theory of general relativity in order to try and prevent a solution which had an expanding universe. Because the problem is, once you say the universe is expanding and there's a beginning, you have to ask odd questions like, what caused it to expand? And the kind of why questions that we don't really have good answers to. So it was much easier to just pretend it wasn't. So a popular theory at the time was called a steady state theory, where other weird things were going on to try and keep things constant, and a lot of fudging happened to try and ignore this result and what it implied. But there is a prediction. Okay? If you're going to say the universe begins in a hot, dense state, this is something that's really important. High energy gamma radiation is around. Okay? So the early universe if the redshift of galaxies is saying that the early universe begins in a very hot, dense state, there must be high energy gamma radiation around. Now, one of the things that would then go happen, so there is a prediction. If it was all there at the beginning, where is it now? What's happened to this radiation? Something that's sort of often sort of like sort of forgotten is that light travels forever until it hits something. So if you're in the deep vacuum of space, a sort of a wave of energy. So let's say I've got a wave of energy. It's just going to keep going, until it happens to hit something. And space is mostly empty. So unless there happens to be an observer in the way, a planet or something, another star or something, then this is just going to keep traveling forever, until someone happens to see it. Okay. And this is something that is kind of important to remember. So back in the early universe, what was around, so if I draw the early universe and it's small, what's in it is high energy gamma rays. Okay? And high energy gamma rays have very small wavelengths. Okay, so we're thinking about the stuff at the top end of the EM spectrum. So you've got radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. So we've got a load of this stuff. This is the high energy end. But as time elapses and as we go through over 14 billion years, well, the actual universe itself is getting bigger. Now the universe is much, much, much bigger. Okay, and as the universe has expanded, the actual physical universe has gotten, has actually expanded in size. Well, the things in it, the radiation in it has also been stretched. These waves of energy, they also get stretched with it. And so what actually happens is these waves become longer. Okay, so actually these wavelengths become longer. And so this gamma radiation, which we start off with here, is going to increase in wavelength, become X-rays, and then it's going to become ultraviolet, it's going to become visible light, it's going to become infrared, and is currently sitting here in the microwave region. As the universe has expanded and cooled, we've moved down to lower energies. And the idea was that if the universe initially was flooded with gamma radiation, not all of it will have been absorbed by any long shot, and most of it's still around. There must be some kind of echo of the Big Bang in existence. That is actually the prediction of a hot Big Bang, that there is an echo of the Big Bang. So, this echo of the Big Bang sitting somewhere throughout space in the microwave region, corresponding to the temperature of space, which is around about 2.7 Kelvin. And this is how it was found. These two fellows are called Penzias and Wilson. And this is a microwave telescope. It doesn't look like the kind of telescope you might imagine. But what they were doing was they were trying to map the sky using a microwave telescope. So they were looking in that part of the spectrum. And they looked all over the sky. But no matter where they looked, whether they looked that way, or that way, or that way, or that way, they found this weird background hiss. They found this weird sort of like, staticky sort of like hiss that they couldn't identify where it was coming from. They didn't know what was causing it, no matter the direction they looked. And it was uniform across the entire sky. And initially, they thought, like most people, they thought, well, maybe our equipment is broken. And they checked their equipment. They cleared out some white dielectric material from the inside of their telescope, which was in fact pigeon poo that had been left by some pigeons that were building a nest in their telescope. And no matter what they did, they just kept finding it. And they contacted a group of theoretical physicists at a nearby university to say, we can't understand why this hiss is there. Has anyone got an idea about what it is we might have found? And it turned out they had found the cosmic microwave background. They had found the echo of the Big Bang. And the theoretical physicists they spoke to were trying to, at that time, they had they had predicted. They were trying to work out how might we go around finding this thing. And the story is that when the theoretical physicists sort of like hung, when the conversation ended, one of them turned to the rest of the group and said, "Well, we've been gazumped because actually these guys had found the thing that they were trying to sit there trying to work out how they found it. So they found something that they didn't know what it was. Someone else explained what it was, and in a journal of Nature, these guys wrote up their experimental findings. The others wrote up what that meant, and these guys won the Nobel Prize for finding it. So they found the echo of the Big Bang, and you can actually see it yourself. If you ever have seen a TV have a static image like this, like an old style television and an old style aerial, what's happening is that all the black and white dots that appear on the TV screen are signals that your aerial is receiving and doesn't know what to make of it, so just sort of portrays a load of black and white dots. And a small percentage of this static screen that will appear is actually radiation left over from the Big Bang. So you can detect the cosmic microwave background yourself with an old style aerial. It's not a lot to look at because it's not really an image of anything, but it is quite cool that if you've ever detuned an old style TV, you are actually looking in part at the echo of the Big Bang from 14 billion years ago. And so in terms of what it is you need to know about the cosmic microwave background, right. So the Big Bang is this. The Big Bang theory predicted that the gamma radiation in the early universe would cool not cool, the radiation itself would, would become lower energy microwave radiation as the universe expanded and cooled. This radiation was found, which is, supporting the Big Bang model? No, Big Bang model. Yeah, and it's called the CMB, or the cosmic microwave background radiation. And it is the echo of the Big Bang. It's not strictly an echo in an echo thing, but it's the leftover remnants of that radiation. You don't need to know a lot of it in huge amounts of detail, but you just need to be able to identify that these are the two things that support the idea of the Big Bang theory. The redshift of galaxies, because everything's moving away, predicting that they were at one point all in the same spot, and the cosmic microwave background radiation, which is microwave radiation found in all in all directions in the universe, which is the gamma radiation that has stretched out as the universe itself has expanded and cooled. And that is what the Big Bang theory is, and it is the evidence for the fact that 14 billion years ago the universe started expanding, and it's been expanding ever since.